The next speaker from across the other side of the Atlantic, it's a pleasure to welcome Anastasia Volovich, who's going to tell us about singularities of scattering amplitudes from Plaby graphs and tensor diagrams. Can you?
Hi, yes.
Great.
Okay, can you hear me? Yes?
Yes.
Okay, great. So first of all, it's great to be here. Thank you so much for inviting me. I wish I could come in person, since I always love to come to Cambridge, where actually my brother and his family live. So I'll tell you a little bit about the exciting connection between scattering amplitudes that we compute in physics and cluster algebras, which is the subject of this conference. Now, the focus of my talk today will be on the singularities structure of scattering amplitudes. And I will present some results from physics of what's known about these singularities. And then I'll try to explain several mathematical constructions of how to get this set of singularities from Plaby graphs and tensor diagrams. And so before I begin, this work is based on the series of papers that I wrote recently. So these are the papers with Mark Spradlin, our current postdoc Akshay Yelishpur-Srikant, my former student Anders Schreiber, who's now in Munich, and two of my current students, Jorge Margo and Li Cheng Ren. Okay, so let me start. So here is the outline of my talk. So what I will start with, I will overview the status and tools for amplitudes computation. So this will be some physics results. I'll present, some of the notations as needed, but basically I'll focus on this physics results of the set of known singularities. So you'll take it as a given. So I'll just show you some lists. And then the question we're going to be addressing is, what is the mathematical structure of this singularity? How can we, from a mathematician's point of view, how can we describe this set of singularities? And the answer, so I'll right away present the answer. So it will turn out that for 6- and 7-point amplitudes, this set of singularities is very nicely described by cluster coordinates. So we'll get these singularities from cluster algebras. And then I'll start increasing the number of points and explain to you some of our recent constructions of getting 8- and 9-point singularities, 8- and 9-point amplitude singularities from Plaby graphs and from tensor diagrams. Are there any questions on the plan? Okay, so we'll start with physics list and then we go on exploring the structures. So before I begin, let me just say, have like an introductory slide on scattering amplitudes. So we will be talking about scattering amplitudes in this particular theory, planar n equals 4 Yang-Mills theory. So there are various reasons it's an interesting and important theory. It's important in physics for various reasons. And it's a nice theory. And the scattering amplitudes in this theory have been computed to very, very high loop order. So on one hand, these theory and the amplitudes in this theory have a lot of remarkable properties, and they've sparked interest from mathematicians working on combinatorics, algebraic geometry, number theory, and here cluster algebra. But on the other hand, the methods that have been developed for these theories have been directly applicable to and greatly helped the computations which are relevant to actual experiments, like LHC physics and QCD theory. So it's not just some toy model that we're looking at. We are looking at this theory, but the goal is really to eventually develop the tools which help the physicists who work on this very difficult computations relevant for collider physics. And indeed, some of the tools that have been developed have been proven to be helpful for real experimentally relevant processes. Okay, so one is interested in, so from physics point of view, one is interested in these scattering amplitudes. So what's known, so now a couple of slides about physics results. So what's known about this theory? So we are looking at scattering amplitudes. So scattering amplitudes are characterized by number of points, number of loops, and the helicity structure. So here I drawn a graph. So you can see this is we call this a 6-point amplitude. So there's 6 external legs. It's a 7-loop amplitude. There's 7 loops in these graphs. And then amplitudes have a helicity structure. And so you could hear sometimes words as MHV, non-MHV, next to MHV, next to MHV. And that just tells you, so each outside leg is labeled by plus or minus. So MHV means there are 2 minuses, and MHV means 3 minuses, and so on. So these are scattering amplitudes in physics, and there are known ways to compute these. These are usually studied in quantum field theory class, in any graduate level or undergraduate level quantum field theory class. There are methods called Feynman diagrams, how to compute them. I'm not going to go into details about that. I'll just tell you that, okay, so in recent years, in this particular quantum field theory, physicists computed a set of amplitudes, and here is a slide of what's known. Okay, I'll have more details about each of these cases on the shortly, but this is like, one list of what's known. So it turns out that for 4 and 5-point amplitudes, these are known to all loop orders, and they've been known for 15 years. Now, the interesting things start happening at 6 and 7 points. So the 6-point amplitudes have been computed through 7 loops, and 7-point amplitudes has been computed through 4 loops. And I refer you to this nice review by these authors. So in particular, James will be giving next talk at this conference. So they have a very nice review summarizing how these computations are done and what methods are used. Then if you start increasing the number of points, so again, this is through 7, if you're looking at all n-point amplitudes and MHV, where you have 2 minus helicity gluons, these have been known for a decade through 2 loops. Now, the recent progress came with the work by Songhee and his group, where they were able to compute a couple new data points. In particular, they computed 8-point amplitude MHV through 3 loops. So that's a reference right here. And 8 and 9-point NMHV amplitude. So that's 3 negative helicity gluons through 2 loops. So as you see, as you start increasing the number of points, the computations become more and more involved. So it took quite a bit. It took a decade to have these computations done. So what are some of the conventions and how these are computed? So again, this is very schematic, but hopefully clear. We're gonna, for these purposes of this talk, we're gonna think of an amplitude as a function of some variable. So function of a kinematic. So what are the variables? So the variables are described by endpoints in a 3-dimensional, in a P3. So you will see everywhere this ZIA. So I labels the number of points, and A is a coordinate in P3. So because of the certain property of this theory, one can build this SL4C invariance. And so you can take 4 of these Z's and make a 4x4 matrix, compute its determinant, and that's what this is what's going to be defined by this bracket. So momentarily you'll be seeing a lot of these brackets IJKL. So that's what these are. So these are the variables of these functions. I'll have all the examples momentarily. Now, what kind of the functions these amplitudes are? Well, the functions are usually multi-polylogs of weight, which is twice the number of loops. So for example, for 2 loop amplitudes, it's a weight 4. So it's like a log to the 4th, Li4, etc. So these are known functions. Now, the goal, so there are many things have been studied in the past several years, but I'm going to just be very focused on this talk. So, and the focus of my talk is going to be the arguments of this function. So I will just talk about the singularities. So there are many, so this is again schematic. So just a set of well-defined set of the singularities of these functions. So without further discussion, let me just summarize for you as we go with a number of points and what's known from physics about the singularities of these amplitudes. Okay, so as you saw here, we start with 6 points. So for 6 points, as I promised, the amplitudes is a polylog function. You see here, I have a formula. So leave 4 of these various brackets. Okay, so and that's the result of it. So think about it as a result of physics computations. Okay, and the computations have been done about a decade ago. Now, so you can just extract the answer from the paper and then ask how do I describe the set of arguments that appears here? Okay, so let me tell you the answer to this. So there are 15 possible brackets, and we're going to call them letters. And the brackets are like 1, 2, 3, 4, as you see here, 2, 3, 5, 6, etc. So, and when you see this, of course, this is nothing but the GR46 Plucker coordinates of the form A plus 1, B, C. Okay, so the set of singularities, I just learned that a set of singularities for 6-point amplitudes is described by 15 letters, which are just Plucker coordinates on GR46. Okay, that's keep that in mind. Let's continue. Let's increase the number of points. So then the amplitude starts looking a bit more complicated. There's a more general polylog function, Li22, which also has been known for a decade. Now, if you look at closely at the arguments of these polylog functions, so in addition to the GR4n Plucker coordinates, which there are 35 of them, there are these quadratic expressions of the brackets that appear, which are denoted, I denoted them by this kind of brackets, and they appear everywhere. So if you look at it, the statement is that the singularities of the 7-point amplitude are described by not just 35 Plucker coordinates. In addition, there are 7 cyclic images of these 2 brackets that I wrote here in red. Okay, so bear in mind, I'm going to increase the number of 8, but of course, since this is a cluster algebra workshop, you might immediately start recognizing what these are, and we'll get there. Okay, so let's start increasing the number of points. Okay, so that's when it gets much more complicated. So these computations were done by Songhee, Li, and Zhang starting 2019. So here it gets quite involved. So there are not just Plucker coordinates, there are also this other expression. So one can open the paper and start analyzing them. I just wrote for you a list. Just keep in mind there's a list. So there are these rational expressions that are only cubic or quadratic in brackets. But in addition, there are also 18 algebraic letters. So I didn't write them explicitly because that would be a whole slide just to write them. But just to tell you, there are these algebraic expressions which would involve the square root of this delta that's written here. So it'll be like a plus square root of delta, where delta is this, and there's also another cyclic of that. Okay, so as you see, it gets more and more involved. So, and then moreover, so the more amplitudes, the more computations are done by physicists, the more data you get. So for example, recently Li and Zhang computed another 3-loop amplitude, and there are yet additional letters, so that I denoted here in white. So there's a list, and just for your amusement, so for 9 points, here's a list. There are 59 times 9 rational letters. So so the expressions for these, and then there are, in addition, 99 algebraic letters involving these types of square roots that are written here. So you see there are square roots of this delta plus 8 more of cyclic permutations of these. So very good. That's the results from physics. So now, why am I here? Well, we would like. So these were computed by some hard methods. Now, when you look at the list, we really like this theory, this n equals 4 Yang-Mills theory, and we'd like to make a mathematical statement. So the main question is, if I give you these lists, what is the mathematical description of these letters? So that's the main question and focus of my talk. So just suppose you know nothing, I give you the list, could you please describe this for me? And indeed, this is why, again, I'm here. The answer at first seems to be that the correct answer is cluster algebras. So the statement is the following. In our 2013 paper with Goldin, Goncharov, Spratlin, and Vergu, we observed that the letters, the set of singularities that I presented for you for 6 and 7 points are given by the subset of cluster coordinates of Grassmannian cluster algebras. So if some of you might have recognized immediately when I showed you the 7-point letters, you could have said, wait a minute, these are just cluster coordinates for GR47 cluster algebras. So that's the sharp statement that was there from 2013. I usually now pause, and for physicists, I start reviewing the cluster algebra constructions. Thankfully, I don't have to do it here. I'll just remind you the initial quiver for Grassmannian cluster algebra, which looks like this. So you just refer to a paper by Scott, Gechman, Shapiro, and Weinstein. So usually I go into introduction and tell physicists what cluster algebras are. So that's the initial quiver mutation rule. So thank God I don't have to tell you this. And so let's look at this. Let's just take this. For 6 and 7 points, so this is the initial quiver for 6 points. We mutate. So for example, we mutate on node 1 for 5. We produce the following quiver. So we produce the coordinates 1, 3, 5, 6. You're very familiar here with this. And of course, we get 14 quivers, and we get all 15 cluster coordinates for GR46. We do the same for GR47. So again, if you of course remember, for GR4n, the initial quiver is 3 by n minus 5. So it's 3 by 6, so plus the frozen nodes. So if you do the same, so you start with the initial quiver for GR47, you mutate, you get 833 quivers. And you look at different set of cluster coordinates, and indeed you get the 47, which contains the Pluka coordinates and 7 cyclic images that I had in the previous page. Okay, so this was great. This is when we all got excited about cluster algebras in 2013, because this independent mathematical construction matches the singularities of 6 and 7 point amplitudes that were computed in physics. Okay, so then, why am I here? So what's been recent? Well, recent is the following. So of course, you very well know when n is greater than 7 for GR48, cluster algebra is infinite. And for amplitudes, of course, if you look at the amplitudes, there's only a finite subset that appears. So we'd like to describe them. Number 2 is usually when we talk about cluster algebras, the letters involves usually are rational functions of the initial coordinates. But here in amplitudes, we have letters that involve square roots. So these are 2 new features that have been the focus of people's attention in the last 2 years. And we'd like to understand this. So there's been several approaches to this problem, and I will only focus on what we've done. So, but I'll just say there is a description based on tropical geometry by Drummond, Papathanassiou, and others. There's a description based on dual, so this tropical geometry is a generalization of Spire-Williams construction from 2003. And then there's a dual polytope, so I have a slide, but I'm not gonna go over this. And then there's a dual polytope description by Arkani Hamed, Lam, and Spradlin, where they use the methods of Fraser and others, where they were able to reproduce these features. There's also a scattering diagrams approach, which I will not talk about at all. And what I will say in the next 10 minutes is I will try to explain to you how to get these letters from two different constructions. One is Plaby graphs and the other one is tensor diagrams. Okay, very good. So
Anastasia, can you hear me?
Yes.
Can I ask an orientation question? Does, in these, for 8 and above, does the number of letters depend on the number of loops?
Yes, it does.
So as the number of loops goes up, you might need more and more letters.
That's exactly what you see with this case of 8 points. So first people computed just 2 loops and MHV, and then somebody came in and computed 3 loop MHV.
So but if you wanted to do all loops, you'd need infinitely many letters.
That's right. Well, no, there is a conjecture, which, there's a conjecture of what the finite set of letters is, yeah.
Okay, thank you.
Okay, so, but eventually, yes, eventually we believe that, again, we believe, but eventually we believe that there is a statement of that the letters are built out of, what is it, 280 or something. I will mention that. Actually, I have this, yeah, I will mention that. Yeah. Any other questions? Okay, so let me just 5 minutes each. So Plaby graphs. So the idea is not new. The Plaby graphs have been used for describing, as applications to scattering amplitudes and describing the integrand of the amplitudes for a decade. There's a book by Nimar Kani Hamed, Bujeli, Kachadze, Goncharov, Postnikov, and Trinker. So that, you know, so this technique is not have been used in physics. So our strategy is going to be very simple. So each Plaby graph comes with a matrix C, which given certain parameterization, you can write matrix C for various reasons, which I'm not going to describe. The building blocks of the amplitudes is described by this following integral, which has a delta function of C times Z. So C is the matrix associated with Plaby graphs. Z are the same Z's endpoints in P3. So the idea is very simple. We start with Plaby graph and solve CZ equals 0 and compare with known letters. So very graduate student oriented process. You know, you don't need to do anything other than linear algebra. So here you just open your favorite program, which parameterizes your graphs and solve for the letters. So before going to 8 and 9, here's 6 and 7. Here we reproduce those 6 and 7 point letters from these Plaby graphs. Now, the reason we were excited by this construction is because we could get square roots immediately. So we would start with this 8-point Plaby graph and solve Z equals 0 for it, and boom, we get a square root, and exactly the correct square root that appears in amplitudes. Now, for 9 points, we do the same. However, if you actually solve, there are extra square roots you get than those appear in amplitude. So one can conjecture that as you go to higher points, you know, one has to in parallel do math computations and physics computations. So one can conjecture that indeed those would appear. But okay, so far we reproduce, and we can, via mutations, we can get even more. Then comes the rational letters, and we were puzzled because we couldn't just get all the rational letters just from Plaby graphs. So we really have to consider non-Plabic matrices. So we would take the Plaby graph, write down the quiver, dual quiver, and then mutate on faces. For example, you can mutate on face F8 in this graph, and you get some non-Plabic C matrix, and then you would solve CZ equals 0 for that non-Plavix C matrix, and it turns out that it is necessary. This procedure is necessary in order to get all the correct rational letters. We will also, along the way, we're getting some non-cluster coordinates, but that we solve because so the way we're doing it now, we're restricting to a top cell. So setting K for the Plaby graph equals to n-4, and then allowing non-Plaby graphs from that, we can get all the letters. So maybe I'll show you the results. For example, for 8 points, we can start from top cell, and then the way we're doing it, we're just starting and then we're mutating. We identify the following 13 mutation sequences, from which we can obtain this extended alphabet of 280 letters. So you've asked about more and more letters. So this gives 280. Now, if I look here, so I had, where is it? I had 180. So there are extra letters, and the extra letters contain this 24. So the conjecture, I think, that everybody thinks is true at the moment, unless counterexample is given, that the n equals 8 alphabet letters are all given by this 280. Okay, so the same thing for 9. So there we had to do the following 15 mutation sequences to obtain the letter. So as you see, this is kind of a phenomenological approach. So we have the data from physics, which is also data that's being worked on, and then we identify the set of graphs that reproduces it. But we don't have a theory at the moment to explain the pattern of which graph to take. So we really just, okay, we mutate this way, we get those. But I wish we had some description, maybe a mathematical description of what mutations to do. So we had some conjectures, but I don't have much more to say. To summarize this part of the talk, so we provided some phenological data, and we hope that future work will shed more light on this problem. So if I have 5 more minutes, can I have 5 more minutes? Yes. Who is the chair? Could I have 5 more minutes? Yes? Hello? Okay, I cannot hear. Can you hear me? Yes? Can you hear me?
In the chat, it says that the chair says yes.
Oh, okay, good. Okay, I thought nobody can hear me. Okay, good. So the second approach to the same problem would be the tensor diagrams. So as, again, this audience knows better than me, that cluster variables can be represented by tensor diagrams of Fomin and Pilevsky. So for example, here I've drawn some examples. Again, for physicists, I usually would have to review this, but not for this audience. So for each diagram, one can associate an invariant by assigning a momentum twistor Z to each node, and an epsilon to each vertex. So for example, for this diagram, the invariant is just a 1, 2, 3, 4. For this diagram, there's an invariant of the form that you've seen. And if you want an invariant for something like this, this is an invariant. So now this tensor invariant is known from work on Fomin and Pilevsky, invariant under graphical moves called Skein relations. And again, this is direct copy from their paper. I remind you that a planar tensor diagram is called a web, and an arisable web is a web that can be turned into a tree diagram using Skein relations. So for example, here is an example of this in practice. Again, I don't need probably for this audience to show you. Here is a diagram. You could show that is equivalent to this diagram via this set of relations. And the conjecture is that the tensor invariants for an arisable web are in 1-to-1 correspondence with cluster variables. So my understanding that this was proven by Fraser for GR39 and GR48, but correct me if I missed any citations here. So, okay, very good. So this is well known. Now, what does that have to do with physics and with amplitudes? So here's what we propose. So in this paper with Li Chen Ren and Mark Spradlin recently, we propose the following. We look at the almost arisable webs. So these are the webs with one inner loop. And then we have a set of rules to assign to them a web series, okay, of something like this. And there's some rules we have in a paper, you can take a look. And we are able to resum this series. And then we show that the series has the following form. And then if you look at the pole of this expression, exactly, so you just solve the quadratic equation that appears here. So we observe the square root, that exactly the square root that appears in this pole is exactly of the form that we need from amplitudes. So for 9 and 8 points, this construction exactly reproduces the type of square roots that we see in amplitudes. Okay, so that's the upshot, very quick upshot of our work. So let me just conclude by just again saying you what I told you today. So we've been focusing on the singularities for n equals 4 Young-Mills theory amplitudes, and they are described by GR for n cluster algebras for 6 and 7 points. Now, starting with 8 points, one needs a mechanism which produces finite subsets in GR for n, and also which produces square roots. So again, from amplitudes, we need finite subset, and we need to be able to get the square roots. So we studied the candidate mechanism. One was from Plaby graphs, and the other one was from tensor diagrams. Of course, in future, it opens a lot of future work. So more systematic needs to be done, more examples. So both amplitude sides and Plabic and tensor diagram sites have to, more examples should be studied. I only focused today on a specific set of singularities on these letters. But of course, eventually, as I showed you in the beginning, we want to write down the actual expressions for these amplitudes. So we want to know exactly the functions. And there are certain properties of also called cluster adjacency. You'll hear probably from Japes in the next talk, start playing the role. So the cluster adjacency structure fixes the actual structure of the final function. We call them cluster functions. So there's even more structure than what I described to you today. And eventually, of course, our goal is to move away from n equals 4 Young-Mills theory. So recently there was some work showing cluster algebras in by Hen, Papathanasiou, and Dima, I forgot, and Dima, okay, and they showed that indeed, for example, some of the cluster algebras appear directly in Feynman diagrams, not just in final amplitudes. So with that, yeah, I'll stop here. Thank you.
Thank you very much. Are there any questions from the room? There may be two.
Just speaking in this.
Hi, Anastasia, can you hear me?
Yes, who are you?
I'm Alistair King.
Maybe you can introduce who you are. It would be helpful. Oh yeah, I see.
I'm on Pierre Guise.
Ah yes, okay.
We're having major problems here.
Communication
problem. I had two questions. One is just ask, are the slides available?
Yes, I will send them.
Okay, and the other one is, when these letters appeared in your functions, they seem to be actually functions of what we call cluster X variables. If you can go back to the very beginning.
Yeah, I should mention this. Yes, that's very important. Yeah, they are X variables, but I was focusing on A variables for the purpose of this talk. That is very important. Yes. Yes. So actually, I spared you from the details. So this is actually a simple alphabet, the P and tensor product, and in function these are indeed X variables. So, but today's talk I just focused on A's. Yes.
Is it because the A's define sort of the edge of the thing you want to integrate over?
Yeah, because A's are easier. Yeah, then you have to then from A's you go to the next step, and when you construct the functions, so you go to you have to construct X variables and then determine the function. So that's kind of so I was on step number 1 of this, and then you go to, so indeed for 6 and 7, these are all X variables, and they're precisely the X variables of the correct cluster algebra. But for the functions for all this other 8 and 9 points nobody really wrote them yet. So that's why. So I focus on step 1, whereas so I focus on step 1 for 8 and 9 points, but for 6 and 7, indeed, much more is known. There's X variables and the actual functions is known. Yeah, maybe I stay like that.
Okay, is there a question online from Nima?
Yes. Hi, Nastia. I just have a question about the sort of general idea that maybe as we go to higher loops, we see more and more letters. That this idea that we should only see finitely many letters has to do with your guys' work, that there's sort of finitely many loci where we expect to have singularities a la Landau equations. But is it possible that that we get more and more letters whose, for example, more and more things that look like A plus root delta, where the A changes, but the delta is always the same? So that the actual sort of solution of the Landau equation would be exactly the same, but you'd get sort of more and more letters. Do you have any evidence for something like that? I mean, is every letter that you're seeing actually corresponding to a different Landau singularity, or could it actually be that these 2 points of view are consistent with all the letters showing up eventually in the answer?
Yeah, so far everything seems to be consistent, but as you know, there's been, when with our students, actually, I was not on that paper, for 2 loops, when we made a prediction for letters from Landau singularities, there was some discrepancy with then Stong actually computed and found more letters. So my answer to this, my honest answer is that I think somebody really has to do the computations. We can speculate as much as we want. It is possible. So in short, it is possible, but I think, I think the actual computations will tell the final answer. But again, for example, here, we do have again an example. So here is the 180, but it's actually 24. When they did new computations, there were extra 20, this is just for rational, the extra 24. Now we immediately went on and started checking that they were indeed on the list of 280 predicted from tropical geometry and from our lists. So everything is possible, but again, I should mention, this is 10th talk I give on this, but I should mention the connection with Landau, because of course there's another description, but since it's a math conference, I didn't. Sure, certainly, yeah. This all should, and indeed there was the prediction in Mark's paper with students for the 8-point case, which later there were some discrepancies, as you know. Yeah.
Thank you.
Okay. Thanks very much. Okay, perhaps we'll draw things to a close here and thank Anastasia again. I suppose if people want to have further questions, they could continue in the chat, but here we're going to go and have some tea. Thank you.
Anastasia, I should mention that there are some questions in the chat that you should look at and a comment.